Now we shall come to the most fundamental law of electricity, and that is Ohm's law. Now, Ohm's law was given by George Simon Ohm in 1828, and it states that the current flowing through a conductor is directly proportional to the potential difference across its two ends, provided the physical conditions like temperature, strain, etc. remains constant. Now here, if you increase, according to this law, if the potential difference across the two ends of the conductor is increased, then the current flowing through the conductor also increases. And mathematically, the Ohm's law is given as V is equal to Ri. And R is the resistance, is a constant of proportionality and is called the resistance of the conductor. I is the current flowing through the conductor. V is the potential difference across the two ends of the conductor. And this R, the resistance, it may also be defined as the ratio of the potential difference applied across the conductor to the current flowing through it. And mathematically, again from Ohm's law, we have V is equal to Ri. So R will be equal to V by I. And this has a unit, and the unit of SI unit of resistance is ohm. It is denoted by this symbol omega, and 1 omega is equal to 1 volt per ampere. Volt is the SI unit of potential difference, and ampere is the SI unit of current. So from the formula, we have the SI unit to be 1 ohm, and that is equal to 1 volt per ampere. Now the cause of resistance. Okay, now by resistance, what we meant is that okay, the resistance of conductor is the opposition in which the conductor has to the flow of current. Now, as electrons moves inside the conductor under the influence of the electric field, they collide against ions and atoms, and their motion is thus opposed. Now, you can recall that if you applied an electric field across the two ends of the conductor, then the electrons will get drifted towards the positive end of the conductor, and upon moving towards the positive end, they will collide with the positive ions and atoms. We know that in a conductor there are free electrons and positive ions and atoms. So upon the moving from one end to another end, the electrons, they will collide with these positive ions and atoms, and thus their motion is opposed. Now this opposition offered by the positive ions and the atoms in the conductor to the flow of electrons is termed as the resistance of the conductor. So here the resistance is due to the positive ion and atoms inside the conductor, which opposes the flow of this of the electrons. So if there are more positive ions, the resistance will be large. If there are less positive ions and atoms, the resistance will be low. So that is the cause of resistance in the conductor. And as we shall learn that resistance is not always constant. It depends upon temperature and some other factors. Okay, that we'll learn later. So now we'll come to another topic, which is ohmic and non-ohmic conductors. Now there are two types of conductors. One are those which obey Ohm's law, and another are those which do not obey Ohm's law. So ohmic conductors, they are conductors which obeys Ohm's law, and the VI graph, that is the potential and current graph of such conductors, is always linear, and the graph passes through the origin. And non-ohmic conductors, they are conductors which do not obey Ohm's law. And for these non-ohmic conductors, the VI graph is non-linear, that is, it can be a curve, or any other way, but non-linear, and may not pass through the origin. Now these non-ohmic conductors, they may conduct current or may not conduct current. Okay, they may conduct poorly or not at all when the potential difference is reverse. Examples of these non-ohmic conductors are diodes and transistors. Now in the diodes, if you reverse the polarity of the potential difference, then what happens is that the diode will not conduct any current. Okay, if it conduct also, it will be a very small current. Okay, so that is non-ohmic conductors. So if you reverse the polarity, they may not conduct any current, and if they do, it will be a very small, which is negligible. So these are two types of conductors, ohmic and non-ohmic conductors, and the properties are that for ohmic, VI graph is linear and the graph passes through the origin, and upon changing the polarity, it still conducts current. But for non-ohmic conductors, the VI graph may not be linear and may not pass through the origin, and upon reversing the polarity, it may or may not conduct electric current. Now the VI graph of the ohmic and non-ohmic is given in the figure. For ohmic conductors, you can see that the VI graph, okay, the potential difference, and the current graph is linear. That is, it is a straight line passing through the origin. And for non-ohmic conductor, you can see that the VI graph, it's non-linear. That is, it is a curve and it does not pass through the origin. Now this is the VI graph of a semiconductor or a diode. And for diode, you will learn in the chapter semiconductors. So these are the two graphs of these two types of conductors. So now we will prove Ohm's law. And Ohm's law can be proven by using the concept of drift velocity and the relation between current and drift velocity, and that we have done in the earlier topics. So here in this diagram we have a conductor of length L and area of cross section A, and this conductor is connected to a potential difference V, okay, to a battery of potential difference V. And upon connecting to this potential difference V, the electrons inside the conductor gets drifted with a drift velocity Vd, and the current will flow through the conductor, and the direction of flow of current is always from positive to negative. And here your E is the electric field between the two ends of the conductor. So using the relation of current and drift velocity, we have I is equal to NAVDE. N is the electron density, the electrons per unit volume. E is the charge of the electron or the elementary charge, and your Vd is the drift velocity. Now the drift velocity, we have found this relation and we have found the expression for this drift velocity, and it is equal to small e, capital E divided by m tau, and this is taken in magnitude only. We are not seeing any vector notation here, so this is just the magnitude only. So putting the value of this Vd in the above equation, NAVDE, we get I to be equal to NAEE divided by m tau E, and that will be equal to NAE square E tau divided by m. And now this electric field, again this is from chapter 2, the relation between electric field and potential difference, and we have done in capacitor that E is equal to V by D. So here also, if the potential difference across the two ends of the conductor of length L is V, then the electric field will be given as V by L. So instead of E, we will write V by L. So we have I to be equal to NAE square, and then V tau divided by ML. Then we can write this equation as V to be equal to I. Upon cross multiplication, we get ML divided by NE square tau A. Now M is the mass of the electron. L is the length of the conductor. We keep it constant. We will not change the length. Now small n is the electron density. This also depends upon the material of the conductor. So here we're using the same material. So n is constant. E is the elementary charge, which is constant. Tau is the relaxation time. Now this tau depends upon the temperature. So we keep the temperature constant. So tau is also constant. And A is the area of cross section. Again, here also we will not change the thickness of the conductor. So your area will be constant. So all these quantity M, L, N, E, tau A, they are constant. Hence, your V will be equal to I R. Now R is the resistance and it is equal to ML divided by NE squared tau A. And this is known as the resistance of the conductor. So you can see here that R has got a value. It is equal to ML divided by NE squared tau A. You should remember this formula since we will study the temperature dependence of R by using this formula. Okay, so hence your V is equal to IR, which is Ohm's law, or V is or I is directly proportional to the potential difference. So this is the proof of Ohm's law. From this formula, R is equal to ML divided by NE squared tau A, we will come to another topic, or we can define another quantity known as resistivity. So here, resistivity or specific resistance, we can define this quantity by using this formula. R is equal to ML divided by NE square tau A. Now, since the number of electrons per unit volume N, which is the electron density N, depends upon the nature of the material, the resistance of the conductor depends upon the nature of the material. So that is one factor in which your resistance depends. It depends upon the nature of the material, whether you're using aluminum wire, whether you're using copper wire, whether you're using other types, another type of wire, silicon wires. So depending upon this nature of the material, your R may be large or it may be low. Then the relaxation time tau. Now this relaxation time tau changes with change in temperature. Hence the resistance of a conductor changes with temperature. So that is another factor in which the resistance of the conductor depends upon. It depends upon the temperature. Now how it depends upon the temperature, we shall do that later. Then again here, if we use conductor of the same material, okay, and keeping the temperature of the conductor constant, then this M divided by NE squared tau, this will be constant. So here we're taking the same material and the temperature is also constant, so N and tau is constant. But we can change L and A. We can change the length of the conductor and the thickness of the conductor, or the area of cross section A of the conductor. So here this constant M divided by NE squared tau, this is called the resistivity of the conductor, or the specific resistance. Therefore, upon putting this value in the equation, R is equal to ML divided by NE squared tau A, we get R to be equal to rho L by A. And here rho is constant. Remember, this rho is constant, and L and A here, it can be changed. So here R depends upon the length and the area of cross section of the conductor also. How? since R is equal to rho L divided by A, R will be directly proportional to the length of the conductor, and it will be inversely proportional to the area of its cross section. Hence, if you increase the length of the conductor, the resistance increases. And if you increase the thickness of the conductor, the resistance decreases. Okay, if you increase the thickness, or which means increasing the area of cross section, the resistance decreases. And we can define this rho also from this formula by keeping L to be equal to 1 meter and area A is equal to 1 meter square. Then R will be equal to rho. So here we can see that rho is equal to resistance offered by the conductor of length 1 meter and area of cross section 1 meter square. So that is the definition of this specific resistance or resistivity. Is a resistance offered by a conductor of unit length and unit area of cross section. And the SI unit, it can be found from the formula itself. It's ohm per meter. That's the SI unit of resistivity. Now we come to temperature dependence of resistivity. We know that resistivity of conductor is given as rho is equal to m divided by n e squared tau, and m and e, they are constant. They are mass and charge of the electrons, and n is the electron density. So if you're using the same material, n will be constant. So here we will be using the same material, so n is constant. Now for this tau, this depends upon temperature. In this case, we shall change the temperature. So here tau will no longer be constant because we are changing the temperature. So hence your rho will be inversely proportional to this relaxation time tau. Now to recall, what is this relaxation time? Relaxation time is the time uh, in which an electron accelerate under the influence of the electric field before colliding with the positive ion. So that time in which electron accelerate before colliding with the positive ions, that is known as the relaxation time. And this relaxation time, it depends upon the temperature. Now if we increase the temperature of the conductor, what will happen to the electrons? This I've told you while doing drift velocity. If we increase the temperature of the conductor, the electrons, they will move faster. So since the electron moves faster, the relaxation time will be small. And if the relaxation time is small, decreases, then this rho, which is inversely proportional to the relaxation time, this will increase. So if you increase the temperature of a conductor, the relaxation time decreases and the resistivity increases. So if you increase the temperature of the conductor, the resistance or the resistivity of the conductor will increase. So that is how this resistance or resistivity depends upon the temperature of the conductor. So the four factors in which resistance depends upon are number one, the nature of the material of the conductor. Number two, the temperature of the conductor. If you increase the temperature, the resistance increases. Number three, the length of the conductor. If you increase the length, the resistance increases. And number four, the area of cross section of the conductor. If you increase the area of cross section, the resistance decreases. So these are the four factors in which the resistance depends upon. Now we come to another definition of conductance and conductivity. Now conductance is just the reciprocal of resistance. Okay, so it's denoted by G and is equal to 1 by R. And it has a unit which is inverse of ohm. And this unit is also called Siemens and is denoted by S. And conductivity is the reciprocal of resistivity. It is denoted by sigma and it is equal to 1 by rho, the reciprocal of resistivity, and the SI unit is the inverse of ohm and meter, or this inverse of ohm is also called mho. So the SI unit of conductivity is mho per meter, and this mho is also called Siemens. So again we have Siemens per meter. So these are the SI unit of resistivity. So we come to the next topic, which is electric energy and electric power. Now electric energy is the total work done by a battery or an EMF source in maintaining electric current in the circuit for a given time. Now if a current is flowing through a bulb, then the bulb will actually glow, and after some time it will also be heated. So if you touch it, it may burn your hand. Okay, so the bulb in this case, it's you can say it's converting this electrical energy into light energy and heat energy. And here in the diagram we have a resistor connected to a potential difference V, and this resistor is a device which opposes the flow of current. It has a resistance R. So in the case of a bulb also, that acts as a resistor. And whenever current flows through the resistor, some amount of energy is being dissipated by the resistor. And from the definition, energy is work done by battery source in maintaining electric current in the circuit for a given time. So here we have 2 points, 2 endpoints A and B in the diagram, and there's a work done in bringing the charge Q from A to B, and actually that work done in moving the charge Q from A to B is given by this W is equal to V into Q. Now this comes from the concept of electrostatic potential difference. So this is from chapter 2, that the potential difference is equal to the work done per unit charge. And since Q is equal to I, Q is related to the current as Q I is equal to Q by T. Hence this Q is equal to IT. So this is from the definition of current. You get W to be equal to VIT. So this is the energy supplied by the battery to maintain a current I in time t in the circuit. And usually this energy is being converted into various form of energy. In the case of a bulb, it is converted into light energy and heat energy. In the case of electrical appliances such as a heater, it is being converted into heat energy. And we have another formula for this one. This is by making use of Ohm's law. If R is the resistance of the resistor, then according to Ohm's law, we have V is equal to IR. Hence, putting the value of V is equal to IR in the above equation, what we get is W is equal to I square RT. So this is the expression of the energy dissipated when a current I flows through a resistance R in time t. Now the energy is dissipated in the form of heat or in the various form like light also. And the SI unit of energy is joule. So sometime this work W is equal to I square RT. This can be expressed as H, the heat given out by the resistor in time t when a current I flows through it. So that you'll be doing in the alternating current. So you keep in mind this formula also. I square RT is the formula of heat energy. Now we come to the definition of electric power. Electric power is just the rate at which work is done by the battery in maintaining electric current in the circuit, and it is denoted by P, and P is equal to W by T. Now W, we have the work done in maintaining current in the circuit is equal to VIT, so we have P to be equal to VIT divided by T, and you cancel T and T, you'll get VI. Therefore P is equal to V into I. Now you can express this in terms of resistance, current and resistance, and potential difference and resistance. So here using Ohm's law, you'll get P to be equal to I square R, And again, using Ohm's law, your I is equal to V by R, so you can write P also as V square by R. So these are the three formula for power. One is in terms of this potential difference and current, another is in terms of current and resistance, and another one is in terms of potential difference and resistance. And the SI unit of power is watt. So from the formula, P is equal to VI, P is equal to VI. 1 watt is equal to 1 volt ampere. Now there are other units of energy which we use in our day-to-day life, and these are known. This is known as the practical units of electric energy, and you can see these in the electrical appliances or in your meter box also, and that energy is kilowatt hour. So we know that the SI unit of energy is joule, and since work done is equal to VIT, the work is equal to PT. VI is the power. So here 1 joule will be equal to 1 watt, which is the unit of power, into 1 second, which is the unit of time. So 1 watt second is equal to 1 joule. Now 1 kilowatt hour, how much is this equal to? We'll have to find it out. So 1 kilowatt hour, this is the practical unit of energy, and this 1 kilowatt hour, this is equal to 10 to the power 3. You're converting kilowatt into watt, so you'll get 10 to the power 3. Then into 60 into 60, you're converting hour into second, so we have 60 into 60 seconds. Hence 1 kilowatt hour is equal to 10 to the power 3, 60 into 60 watt second. And upon multiplication, we get 1 kilowatt hour to be equal to 3.6 into 10 to the power 6 joule. Remember this relation here. 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joule. This is how we'll convert kilowatt hour into joule. So this unit is actually used for building electrical energy, and as I've told you before, this is found in your meter box. So 1 kilowatt hour, this is also called the Board of Trade Unit, BOTU, or unit of electricity. So these are units of energy and power, and especially power. You can find the unit of power in the electric bulbs, where you have 5 watts, 10 watts. So these are all unit of power.